these lectures that I'll talk about will be about generalized global symmetry, which is a concept that has played an important role in recent developments in quantum field theory. But since we have several days and several hours, the first lecture will really just be about global symmetry. And I'll start with some extended motivation for why we might want to generalize notions of global symmetry. So what are the kind of problems that we're going to try and solve? So motivation. I'm not sure if this is big enough. Is this legible to people in other parts of the country? Okay, so what do we want to do? We want to constrain RG flows. So this is a study in quantum field theory. So our goal is to constrain RJ flows. So we will have some UV quantum field theory, and there'll be some flow to the infrared. And what are the typical kind of examples to which the techniques will apply that I'll hopefully tell you about? So the typical examples that we'll talk about will be gauge theories, in 3D or 4D. There are, of course, other examples that we could study, but these are really of maximum physical interest. And to keep matters most exciting, I don't want to add any additional ingredients. So sometimes when we're studying these problems, we often say, well, this is too hard. Let's add supersymmetry. Let's do something else. But really, I want to study non-supersymmetric 3D or 4D gauge theories, finite n, kind of the most complicated dynamical question that we have access to. Okay, so let's zoom in on two particular problems that have been recently studied. So in 4D, we'll consider SUN Yang-Mills with no matter. I should leave this number, right?
Well, couple those. Yeah.
Okay, SUN Yang-Mills with no matter. What do we know about this theory? Well, it's believed that it's asymptotically free. And that means that the infrared is gapped. Theory is confining. That's one thing. We also know that the physics is labeled by some parameter theta. Theta is the theta angle. So very ambitiously, we'd like to know what's going on as a function of this theta.
By what's going on, you mean what is the phase structure?
Yeah, so let me clarify. So good. So I said here the IR is gapped. So let's now introduce a notion that is important. So if you have a gapped system, it could be trivially gapped. Okay, so the most boring thing it could mean is trivially gapped. Trivially gapped means there's a single isolated ground state. All operators, both local and non-local, are trivial. Just a completely empty theory. But it could also mean, more interestingly, a topological quantum field theory. And these kind of lore about these theories don't really distinguish very much between these ideas.
So you might have more to say, of course, on this, but when you say topological quantum field theory, say in 4D, what do you might have in mind? Some analog of John Simon's theory in 4D?
Simple examples of topological field theories in any dimension, kind of go-to examples, are discrete gauge theories. That's a good example. So
In the continuum.
in the continuum, yes. Yeah. So you could, for instance, write an action like where B is a 2 form and A is a 1 form. And this path integral over B enforces a constraint that sets the flux of A to 0, and so A becomes a flat connection which describes a Zn gauge field. So this is a Zn gauge theory. And more generally, by increasing the form degree here, we can describe a Zn gauge theory in any space-time dimension. So this is an example of a topological field theory that exists in every space-time dimension. That's something that we could have encountered here. But there may be others. In 3 space-time dimensions, we have pretty good handle over what's the landscape of topological field theories. In above 3 space-time dimensions, we don't really know. We just know some haphazard examples.
So 3 space-time dimensions, it's basically Chern-Simons theories and their various overfolds and so on?
Yeah, exactly. Yeah.
More abstractly, what you give to you mean theory with finite dimension with inverse space as opposed to a single dimension inverse space that is trivially gapped.
Yes. Yeah. Yeah. Trivially gapped means that the Hilbert space on any spatial manifold is one-dimensional. Okay, so
What about this as in Zn? I mean, A and B are presumably continuous variables.
oh, how do you see that this is Zn gauge theory?
Yeah.
You should study the observables in the theory. So what are the observables? So for instance, there are Wilson lines and Wilson surfaces that are integrals of B, and you should study their correlation functions. And what you'll see is that the Wilson surfaces are identified and Wilson lines are identified mod n. That's how you'll see the Zn.
That's a wonderful question. About this trivially gapped theory. So if you have some theory which has ground state degeneracy, but it has the same ground state degeneracy on any spatial manifold, what is the progress?
So it has ground state degeneracy on any
Like, suppose there are 2 ground states, no matter what the spatial manifold is.
I don't know any theory like that.
He's saying it's a spin up, it's a bit times the trivial theory.
I mean, maybe we would say that it falls apart into 2 trivially gapped theories. Then, okay. So, what do we mean when we say we want to understand the physics as a function of theta? Well, the first thing we could try and do is distinguish between these various possibilities. So, here's an interesting claim that was recently established in the literature by Gayotto, Kapustin, Komorgotsky, and Seiberg. So the claim is that at theta equals pi, the IR cannot be trivially gapped. So there, in particular, there must be a non-trivial TQFT. Okay, so one of the this is a kind of motivating problem. One of the things I hope to do in the next few lectures is to teach you how to prove this claim.
Wait, either there's a TQFT or there's genuine degrees of freedom.
Or yeah, yes. So if you believe the lore that it should be gapped, which there's a lot of lattice evidence for, at least at theta equals 0, then you might guess that that the simplest possibility is that it's a TQFT. But indeed, we don't, since it's much harder to simulate, maybe impossible to simulate theories with a theta angle, we don't really know. But at the very least, you know this. Okay, so this is a thing that we'd like to prove. So I'll teach you how to prove that. Okay, what's a problem in 3D? I think is interesting. Suppose you have n Dirac fermions. So I here is 1 to n, and this is a spinor index. So they transform in a fundamental of an SUN symmetry. And at least if the fermions are free, there's also time reversal symmetry.
Just ask one more.
Please, yeah.
So since we are going to be making statements about the degeneracy on any manifold, if we take UCD, there is the strong coupling scale which comes with the theory, and we could consider manifolds where the size is, there's a dimensionless ratio then. You can have circles and so on which are bigger, smaller than that strong coupling scale. And when we say something is a TQFT, we mean...
So, when we have this...
It's a very rich question, that's what I'm...
So when we have these ideas in mind, we imagine first going to the infinite distance limit. So by this, I mean first go to the infinite distance limit, below the mass scale of any mass scale in the problem. And then in that infinite distance limit. So it's really just a question about the ground state structure of the initial theory.
Thank you.
Isn't there an anomaly in time reversal symmetry order?
Well, that will be related to what I'm saying. Yes. Indeed, that's an important observation in what I'm about to say. So let's consider, but let me not say those words yet because we're going to build up to that. So let's consider these fermions. So there are n of them. They have some SUN symmetry and they have time reversal symmetry. And we could consider adding, giving these fermions some interactions, either by some Chern-Simons interactions or coupling them to scalar fields or anything you have in mind. Okay, so let's add any interactions plus other fields, essentially other fields, but I want them to be uncharged under SUN. And I want the interactions to preserve T. Okay, what's an interesting claim that you can make? So here's a result due to Senthil and myself and Toshen Sin. In the IR, we can say one of two things must happen. So either T is spontaneously broken, or the theory is gapless. So, or there are massless degrees of freedom in the infrared.
So in other words, you can't have massless degrees of freedom and T being unbroken.
No, you can have massless degrees of freedom. One of the two is true.
So if it's gapped,
So if it's gapped, T must be spontaneously broken. Or if T is preserved, then the theory has massless degrees of freedom.
But it could happen that both happen. That has massless degrees of freedom and
Sure.
spontaneous.
Sure, yeah.
At least one of these two.
Yeah, at least one of these two, yeah. Yeah. Okay, so this is another problem that I'll try and give you the techniques to try to prove. I mean, this is, you should be a little bit surprised about this in the sense that usually we don't have techniques to prove that things are gapless in the infrared and 3D. So that's why this is supposed to be a striking statement. Okay, so these are two interesting motivating problems. And now we'll sort of set up a general machine over the next few days that can address problems like these.
And you say you don't have techniques to prove that things are gapless because there are no continuous anomalies.
That's the main point. And somehow the little parity anomaly here is doing enough of the work. That will be the point. I didn't discuss what that is yet, but that will be the point.
I mean, you don't have continuous anomaly.
Yes.
That's right.
If you have a continuous anomaly, then either has symmetry to be broken on their axis.
And then in either case, they're gapless degrees of freedom. Right. Okay. So we'll now review some of the things that were just being discussed and some of the basic tools that one uses to prove statements like this. But these are some of the motivating types of questions that we'd like to understand. Okay. So what are the tools going to be? So we'd like to find RG invariant quantities. So what are RG invariants? Well, as has been already anticipated, they are what are sometimes called 't Hooft anomalies. So I'd like to review what those are now and develop a perspective on them that will be useful later. Okay, so before we get to this more sophisticated invariant, let's start at a more basic level. So a basic RG invariant actually is just symmetry. What does that mean? So if you have the Hilbert space of the theory, if you have a theory with a symmetry G, and you have the Hilbert space of the theory, then the Hilbert space is a representation. Now, the infrared Hilbert space, the subset of low energy states, sits inside here. And so this should also be a representation of the global symmetry. So one very elementary RG invariant is just the statement that if your UV theory has a symmetry, then the infrared should also have a symmetry. Now this might not be very powerful because it could be that all the objects in your theory that are charged under the symmetry are massive, so maybe this could be the trivial representation.
So the symmetry could be spontaneously broken.
It could be spontaneously broken, and then the Goldstone sector will realize the symmetry nonlinearly. So we should talk about operators if we want to really distinguish that, but in current algebra, I'm being a little bit loose here. Okay, so let's probe this at a little bit of a deeper level. So we can probe the symmetry action by coupling to background fields. So let's consider adding to the Lagrangian a term where we integrate over space-time a mu j mu. This is the conserved current. And this is a source gauge field. It's classical, it's not fluctuating. It's some fixed dynamic, some fixed background that I put into my problem. Okay, and so from this, we define a partition function, z, that depends on a, which is the path integral in the presence of this coupling. And this is the generating function of current correlation functions. So from this object, by taking functional derivatives, we can compute correlators like this. So in particular, it contains the action of the charges, but it also contains more interesting information, the whole current algebra. So it's more sensitive, for instance, to the issue that you're talking about spontaneous symmetry breaking. This is a better thing to study. Okay, so let's talk a little bit about some of the notions that we introduced before. So, for instance, we could ask, what does it mean for a theory to be trivially gapped in terms of that partition function? So, in general, so typically, z of a, or I guess I should say log z of a, if we try to write an effective action, is non-local. That's because the correlation functions that we wrote there are non-trivial at separated points. So this expression should be non-local. So one consequence of saying that a theory is trivially gapped, so in the IR, if trivially gapped, log z is local. So that means if we think again about this object as a generating function of current correlators, that in a trivially gapped theory, the operator J is redundant. Its correlators reduce just to contact terms. Sometimes such a thing is called an SPT phase. Okay. Right, so this is a local and function of A, which is of course also gauge invariant.
You're saying that theories in which the J-mu correlators are contact terms are SPT phases. What distinguishes these from phases that are not at all completely trivial, not an SPT?
So this could be the identity. It could be it could not depend on A at all. That's correct. Yeah. SPT, I mean, SPT is just a generalization of what we used to call classical field theory. Right? It's just some classical action for the background source fields. And so this is a particular instance of that.
Suppose you had a Maxwell term here. F mu nu, F mu nu.
Mm-hmm.
Would that qualify as trivial or not?
Yeah, I think so.
Would be trivial.
Yeah.
So something that's non-trivial is, you tell us.
Something that's not, to get something non-trivial, well.
You want a theta term or something like that?
No. I mean, anything that can be expressed as a local classical action counts as trivial.
So it counts as gapped, right? But
Even trivially gapped, right? Because the partition function is just some phase on. Right? So on every manifold, the partition function is just evaluate the classical field, and you get a phase when you plug in the action.
And that's trivial. So
That's called trivially gapped.
And this being f wedge f with some value of theta, you also call trivially gapped.
That's correct.
Okay.
Yeah.
How would Z of A distinguish between trivially gapped and finite dimensional vector space?
So trivially gapped in a finite dimensional. So in order to get something that's non-trivially gapped, you want the partition function to not always be a phase. So you want some, morally speaking, what you want is some dynamical field at low energy, something that you actually sum over to do the path integral. When I said, when we got to this stage and I said it was a local function of A, what I mean is that it's just a classical action. You just evaluate some function of the source and get a number. You don't do any sum over any fluctuating fields. non-trivial theories would even non-trivial TQFTs would more or less still have fluctuating fields that you would still sum over. For instance, discrete gauge fields that we would sum over in the infrared.
And would depend on the manifold. So.
Exactly. They would have some, and so the partition function would not always be a phase. So the lingo when one describes these things is something if you're in the condensed matter world, you call it an SPT. If you're in the math world, you call it an invertible field theory.
So just to make contact with the condensed matter talks idea, my understanding was that when people were studying these topological insulators, they did this, and then when they got a theta term with theta equals pi, they called it non-trivial.
No, So what's being discussed there is what in high energy physics is called anomaly inflow.
Mm-hmm.
So you have a trivially gapped invertible theory in d+1 dimensions. And then you ask, what are the possible edge modes for it? And in general, the edge modes cannot be an invertible trivially gapped theory.
So the bulk is trivial.
The bulk is trivial in this definition. It's just classical action. But it doesn't support non-trivial.
The implication of the theta is that the boundary would be non-trivial.
Exactly.
What is a non-trivially gapped phase called in condensed matter literature?
A non-trivially gapped is some long-range entanglement or usually something like that. They have various acronyms. I don't know all the definitions, but
And then if it were non-trivially gapped in the sense that you had boundary excitations, you could couple the boundary excitations to a boundary probe and presumably get a non-local action for the boundary probe, right? It would be localized on the boundary but non-local.
so having a trivially gapped, here's maybe the source of the confusion. A trivially gapped theory may sometimes only have edge modes that are non-trivial.
It means in the bulk, trivially gapped.
Right, trivially gapped means in the bulk of space-time. On a closed manifold, the partition function is always a phase, for instance. But it could be the case that if you cut the theory, you have a manifold with boundary, there could be something necessarily living at the boundary. So the typical example is 3D Chern-Simons theory, just U1 Chern-Simons theory, ADA. So on any not dynamical Chern-Simons theory, we're not summing over A, it's just a classical field. That is a trivially gapped theory in the sense that A is a classical field, the partition function is just a phase, the Chern-Simons invariant of the fixed classical field. But if we cut the path integral, we'll find necessarily a chiral boson living at the boundary.
Even in the classical system where you were not summing over?
Yeah, if you want to preserve the symmetry with a boundary condition, you can't have a trivially gapped boundary condition.
Just because Chern-Simons theory is not gauge invariant.
Mm-hmm.
Right, exactly.
I don't understand this partition function is a phase. Even if the actual log CA is non-local, you're just plugging in a background value of A. So why is it not going to be a phase?
Sorry, it's important that it's both local and a phase.
Why is it not a phase in the first case?
In the first case, it's not local.
Okay,
So here the emphasis is that it's local and always a phase.
okay, so then you don't really need to say the phase bit when you're drawing this distinction, right? I mean, I don't understand what you're telling me that's new when you say it's just a phase. It's always a phase, right? I understand if you're drawing a distinction between it being non-local and then being local.
No, I think I think what you're saying is not right. I think the partition function of a general quantum field theory on a general manifold is not always a phase. Z is not always a number of modulus.
See, he's saying a sum over phases is not a sum over e to the power I theta is not e to the power. So you're summing over in different configurations of the low energy field. Each configuration is e to the power I theta,
Right.
but that sum is not. I think
That's correct. Yeah.
I think what you are speaking about this log C, once you compute the effective action, and then it's classical, and you think about...
No, but this, I mean, if we got this by doing a non-trivial sum, it will in general not have modulus 1. Right? Imagine that A has always been a classical field, but imagine there's some other dynamical field B in our problem. Okay? Then we have some action that depends on A and B, and the thing that is well-defined phase is the action for fixed A and B. e to the I s of a and b. But then we're going to sum over b. So we're going to sum over a bunch of different phases. And in general, we won't get a phase. Right? What happens here is that we don't have to do any sum anymore.
And when you say phase, you're working in the Lorentzian way.
Yes, yes, sorry, yes.
It's very unusual.
Yes, I'm a pioneer. Okay. Okay, so more questions about partition functions. There's a lot of terminology and a lot of lingo here. Any other questions, confusions about this?
So the integer bottom-on effect is usually thought of as a topologically it's not an SPT phase, and it's said log ZA is ADA.
Yeah, that was the example I was giving here. That the bulk theory is ADA. That's a SPT, a trivially gapped phase. But on the boundary, if we want to consider a boundary theory that also has this U1 global symmetry, it will necessarily be gapless, actually.
But since you bring it up, just to make sure I understand, isn't it that the bulk theory is the sum, is an integral over all A with the weight e to the I A dA? It's
No,
just
no,
a
no.
classical-
No, it's just a classical. It's just anomaly inflow, right? There's the Chern-Simons theory on a manifold with boundary is not well defined. So in order to cancel that, you need something on the boundary.
I understand that, but you mean the bulk theory is not a path integral?
It's not.
This is the A corresponding to the U1 global source, global symmetry.
Right.
It's just a fictitious object.
Okay, okay.
Generating function of correlation functions object.
Oh, I see. I'm sorry. Oh, okay. This would be a source for the
Yeah.
bulk theory.
Yeah,
Okay.
it's the source for the boundary theory is the chiral boson. It's in particular got a U1 current algebra. And this is the background gauge field for that current.
Okay.
So for the Hall effect, it will be like the magnetic field, some magnetic field. Right?
Yeah.
Okay. I see. Sorry. Yes. Mm-hmm.
More questions? Yeah. Okay. So we have some language about partition functions now, and now we can ask about current conservation.
Sorry, I didn't understand your answer to Madhu's question. So this point is there's two different distinctions: local versus non-local, and real versus imaginary. Real versus complex for log Z.
Okay. Yeah.
So what does local versus non-local mean, and what does real versus complex mean?
Local, if we're thinking in terms of, the simplest setup, which is what I had imagined here when I wrote A mu, J mu, is that we're discussing a continuous global, say U1 global symmetry. And then local means that it can be presented as the integral of some local functional of A.
Okay, I know how it's defined. I meant like what does it mean particularly?
Oh, so it means that, so think of this quantity Z as the generating function of current correlation functions. So if the action, this effective action is local, it means that those current correlation functions are only non-trivial if the currents are at the exact same point in space-time. So it means the currents are, the current correlation functions are contact terms, and so J reduces to a redundant operator. Up here, if it's non-local, then it means the current is a non-trivial operator. The current correlation functions are non-trivial at separated points. So does that answer your question?
So then why do you have to start talking about whether log Z is real or complex?
So it could be the case that we flow to a theory where J is a redundant operator, but nevertheless the partition function is not always a phase.
And I see. So you're saying trivially gap is local and the log Z is real.
Yeah, trivially gap mean this is a local functional of A. So in particular, it's a phase in this case. That's all I'm saying.
Are you saying it's possible that it's a local function but not a phase? Is that what?
For non-trivial gap.
For non-trivial.
Sum over discrete degree.
I think if I understand it rightly, I think he's saying that it could be sum over e to the power I local phases.
Yeah.
So suppose you had a topological quadrilateral.
You mean common source.
Yes,
There's
yes.
no issue of summing over A.
No, but suppose there's some
But the-
topological degree of freedom. Then for each value of that topological degree of freedom, you get some local function of A. So you get e to the power I, that local function, but you have a sum over those things. I think that's what he wants as the
Yeah.
counterpoint.
Yeah.
Okay.
Sorry, I'm not explaining it well.
No, you have explained it perfectly.
And the same with the boundary degrees of freedom, I guess. You are left with a sum over the boundary degrees of freedom. Then again, it's the same issue of e to the power I, various things, and sum over them. As a result, you don't have.
As a result, it's not a phase. That's correct.
As a result, it's not a phase.
Yeah.
So whether it's discrete degrees of freedom inside the bulk or boundary degrees of freedom on which you have a sum left over, is this.
Yeah, in general, when the partition function is not a phase on every manifold, there's something non-trivial there. It could be gapless, it could be gapped, but you can say for certain that there's something non-trivially gapped. The hallmark of a trivially gapped system is that the partition function on any manifold with any background on is a phase. That's kind of the mathematically precise definition of it.
And how do you distinguish the spontaneous picking of symmetries using current coordinates from deep interaction?
Using current correlators. Well, J mu will create a Goldstone boson in that case.
So 1 point function.
But did you mean spontaneous token or discrete symmetry?
No, the one that A is source for.
Yeah, discrete symmetries are harder. We're going to get there. Okay, so let's move on to current conservation. I'll put a question mark. Okay, so we started with a symmetry. So what did that mean, really? We're working towards understanding 't Hooft anomalies in a reviewed way. So we started with a symmetry. So that meant that the divergence of the current is 0. And of course, here I should stress that this means when the source A is 0. That's really what we know. Now we're interested in this partition function that depends on A. So we should investigate this equation where we turn on A. And more generally, we can have that the divergence of J mu is some function of the background field A, some local function. Okay, so this is typically called an anomaly, and I'll try and define things a little more precisely in a minute. I want to stress, though, that so we physicists are not very good at picking our language. We generally call many very distinct phenomenon anomalies. So here, for instance, I am not considering things that are called ABJ anomalies. So in an ABJ anomaly, the divergence of the current is non-zero when all sources are off. The current is really just not conserved anymore. There is no global symmetry. The Hilbert space is not in a representation of the symmetry. So for those things, we just don't talk about them anymore. Here,
Maybe it's worth saying that ABJ is Adler, Badi, Jackie, not Aroni, Bergman, Jafes.
I'm actually old enough to know that. Yeah, that's right. Yeah. Okay, right. So, so unfortunately, sometimes people discuss anything that appears on the right-hand side as an anomaly. But it's the physical implications are crucially different depending on whether or not this condition is satisfied. So if this condition is not satisfied, the current is not conserved, there's no symmetry. If this condition is satisfied, there is a symmetry. The Hilbert space is in representations of that symmetry. So this is the case that we want to focus on. Okay.
Previous thing is also sometimes called gauge global. Gauge global anomaly.
Yes, gauge global, it's horrible. Gauge global anomaly, that's also an anomaly, and then there's various mixed anomalies of other types, and it's horrible. And then this is a 't Hooft anomaly, which couldn't we have invented a different name for all of these different things?
And the previous case might be a duality frame in which it's just
That's
the
correct.
symmetry is just gone.
That's right.
It was never there.
Yeah, it's actually a happy accident of the real world that the real world is sufficiently weakly coupled that the ABJ anomaly is useful even in QCD. But that's kind of an accident. In a different context, it might have it might not have been useful.
It's just not a symmetry.
Yeah. Exactly. Okay, so anyway, we're interested in things that are actually symmetries. So we demand, first of all, that when all sources are off, the current is conserved. And we look at deformations of this equation that can happen when the sources are on. Okay. So a little more technically, what this means, since we've been talking about current correlation functions, so in here, so in this correlation function and others involving J, this condition here means that J mu is conserved at separated points. So
which condition? Del mu J mu.
Del mu, yeah. Sorry, this one, the fact that this is true and that the violation of conservation is only by a function of the source, it means that in this correlation function, this operator is conserved as long as this point doesn't hit any other points.
Because the right hand side is low.
Right, exactly. Yeah. So that means that's the sense in which this is a good condition. If this were non-zero as an operator, then the d mu j mu would just have general correlation functions at arbitrary points, and that's why it's not a symmetry. We don't study it. But here, the violation is very mild. It's only at coincident points.
Why do they compare need to be open?
That's the modification that we're studying. So we're only going to study that.
But isn't the consequence of consistency condition?
You might be able to prove it with the Wess-Amino consistency condition. I'm not certain. Okay, so
Generally, even if Toby Jimmy equals 0, it is 0 in the presence of the background field, you expect there to be contact terms, right?
In the word.
In the correlator?
Yeah.
yes, so this is so you ask how to distinguish?
Yeah,
Yeah, good. So the Ward identity says that the divergence of J gets a contact term when it hits a charged operator. But J is not a charged operator. This violation says that divergence of J gets a contact term when it hits another J. So that's the anomalous Ward identity.
But this difference is only true in, for example, the Abelian theories. If there is a non-Abelian symmetry, J will be.
No, I mean the form of this function predicts exactly the form of the contact term. So we can investigate that, and we'll find that it is different from the one in general implied by the charged operators.
And you get an additional piece. You
Yeah.
always get that what I did
Yeah.
plus something.
Yeah,
That's right.
that's correct.
So, this fact that this right hand side is particularly conform, particular type is comes from the fact that you have a particular kind of structure for correlation function for J's. The divergence of lots of J's has some structure of multiplying, lots of Dirac-Delta function are getting multiplied.
Sorry, say the question. What's the question?
So I am saying that when you are writing this divergence of J is some functional of K, that essentially follows from if you have current correlators like this current correlator and you have a divergence acting on it, that will have a particular kind of structure in terms of Dirac-Delta functions.
Yes, and that structure is predicted by this function.
You're saying that tells you that it's just too open.
Yeah, essentially, if you have that particular structure for current correlators, then that completely determines A. Or in the other way, that if you know f of A, then you know this particular correlation function.
But how did you know a priori that the structure for current correlators was delta?
Yes. So my question was that is it already forced by its consistency conditions that you have to take only this particular kind of particular?
Well, I think that's Abhijit's question, and I said that I wasn't certain. I thought that you might be able to prove it with the Wess-Amino consistency condition, but I'm not sure.
I mean, a typical situations you have you have if you've got something where classically there's no f of a, it comes from regulator effects. Right?
Yeah, and then it will
That
be,
forces
right, that's right.
this to be considered.
Yeah, so indeed. Okay, so this,
I think that forms of invariance. Would it restrict J is correlative, the contact correlative to J of a particular form?
certainly not just scale invariance, maybe special conformal in some way that I don't see, but I mean, you could envision arbitrarily horrible things there, but let's stick to the local f of a. Okay, so one consequence of this is, so recall that we had, of course, we had in the Lagrangian the term integral of j mu a mu. So if the current is not conserved in the presence of background fields, there's some violation of gauge invariance. Now, again, we should clarify our language. A is a classical source. So whether or not the partition function is gauge invariant, I don't really care that much. Right? So I'm not summing over A. So this is not really any significant problem, but it's an interesting feature. Okay, so we could try to adjust this. So our partition function isn't gauge invariant. So we could try and adjust it. So what will we do? So we'll take z of a, and we'll redefine it to be z of a times e to the I integral of something that would be called L counter term of a. This is a local function, and this is not necessarily gauge invariant. This is just a redefinition of what it means to couple to a background field. And by doing this, I can adjust the gauge variation of the anomaly, the gauge variation of the partition function. So. So the interesting anomalies, the things that are really fruitful, are essentially the equivalence classes that you get under these modifications. And these are what are really called 't Hooft anomalies. So you can think that here what I did is I changed my scheme. I changed, say, the counter terms for A, for J, right? Modifying the action by some local functional of A is the same as changing the counter terms for these current correlation functions, in some way that's up to me. And using that, I can modify how this anomalous behavior appears. And so I want to allow myself to do that as I like. And the interesting anomalies are the ones that cannot be removed by such a transformation. Those are what are truly called anomalies. Okay.
Moving from one regulation scheme to another will anyway
That's
effectively
correct.
switch this.
That's right. Every time, if you and I differ by some regulation, some regulator, we'll have such terms.
So we have to look at things modulo that because
Right.
it's not well defined.
That's right. Okay. Okay, so the right, so the typical example, maybe just to flash in everyone's mind. We could have 4D with some Dirac fermions. I, which goes from 1 to n, some n Dirac fermions, and they could have charge qi under some global symmetry. And then we would compute this triangle diagram with 3 current insertions. And we would find that d mu j mu, well, is some number that I won't get right, times the sum over I, qi cubed fa wedge fa. It's a typical anomaly. Okay.
Since we are talking about counter terms, can I ask you something?
Yes,
now?
please.
I know this for a fact for the AVJ anomaly, allow me to mention it, but I thought it was true also for these triangle diagrams, that you could, if you allow yourself a choice of counter terms, you can trade the Toft anomaly for a Lorentz anomaly. That is, if you wanted to preserve Lorentz invariance, then you're forced to have this. But so that you could trade one of against the other. Is there a statement something like this that?
Well, that would probably, if that, I'm not sure if that statement is true, but if it's true, that will mean that there is a Lorentz violating counter term that I can put here that will remove the anomaly.
Yeah.
So, but that's something that can be explicitly checked because.
Right. So when you're saying it's modulo this, are you saying modulo this subject to some symmetry considerations of the counter terms?
Sorry, just a quick comment. In the hydrodynamic context, where we take the theory on with the time circle, in fact, we showed that you could get rid of the anomaly by violating this 0 I thing. And that was necessary from hydrodynamics because everything was you got an effective action, the slope including the conflict.
But I mean, it's kind of wrong to say that you'll get rid of it in this because the violation of the Lorentz invariance will also have the same coefficient in it. So you can push it around, right?
So you can. I was just asking about the precise statement given you can push it around.
Yeah. But so that's, I mean, that's generally the case here also, right? Using this counter term, I can push around the presentation. More generally, I could have bunches of symmetries with mixed anomalies, and I can push around which current has a divergence using this kind of stuff.
You have sources for all the symmetries, and then you have classes for all symmetries.
Right.
Okay.
But in the appropriate cohomology, there will always be something non-trivial. Okay, so good. Okay, so why this long song and dance about anomalies? Well, the reason is, as I stressed at the beginning, anomalies are RG invariants. So let me just give you a very fast, slightly hand-wavy proof of that.
Sorry,
Yes.
so in this case, the reason why you can't get rid of this by writing a local thing is because it has a necessarily 5-dimensional representation when you want to integrate this in and want to write this in.
Yeah, good. So this is related to the question, this clarification discussion that Shiraz and I were having about insulators and boundary terms. So it's, as far as we know, always the case that every anomaly can be removed by a local gauge invariant counterterm in one higher space-time dimension. So you could remove this by coupling to a 5-dimensional Chern-Simons term. But that's 5-dimensional. So here, this counterterm was in the same space-time dimension that we were in to start. Okay, so the claim is that the anomalies in the way I've defined them here, they match on our G flows. So how do you prove that? So let's consider the partition function of A, and let's also include a background metric. It might be the trivial metric. And we can take g to e to the sigma g. And by taking sigma to be large, we can implement our g-flows in this way. So we can scale up space-time. Okay. Let's examine the so-called Wess-Zumino consistency condition. The Wess-Zumino consistency condition is really just a kind of trivial statement about partial derivatives. So it says that partial derivatives commute. So let's consider, first of all, the lambda variation. Lambda is this parameter that I introduced here. It's probing whether the action, the effective action is gauge invariant. So we'll first take the lambda variation. And then we can also take the Weyl variation here. So what is this? This is the Weyl variation of the anomaly. So this is the scale dependence of the anomaly. So the Wess-Zumino consistency condition says that I can change the order of derivatives here. What does this do? Well, taking the derivative with respect to sigma introduces the trace of the stress tensor. Now, this should be 0 because the stress tensor is neutral under every global symmetry.
Why is it sigma times that? Just del sigma log z should be TA, right?
Yeah, I think that sigma should not be there because it's already sigma is already a logarithmic derivative, isn't it?
Sigma is already a logarithmic derivative. Did I mess that up? Yeah, maybe you're right. Okay. Okay, but the point is that this this lambda variation of TA is 0 because this is the stress tensor is uncharged under every symmetry. So this is a general, slightly hand-waving, slightly formal proof, but very general argument showing you that all anomalies. I mean, here I wrote it as if this was continuous because we were discussing that. But more generally, we could have imagined that we had any kind of global symmetry. This was any kind of gauge transformation. And as long as the stress tensor is uncharged, we'll get 0. So anomalies match. There are actually 1,001 ways to prove that anomalies match, but this is one way. Okay.
It's very elegant, you know. I mean, Tuft has that nice argument where he added extra matter and all that. So this is very nice.
Well, I think Wess-Zumino was after that, right? So.
No, but Tuft already had the argument, you know, the basic
Yeah.
argument that the
Oh yeah, of course. That's why it's called an Tuft anomaly.
Right, right.
Yeah.
But I mean, that's also a very elegant argument where
Yes.
you add the extra matter. To
Yes.
the rest.
And another way to do it, which is quite similar, is if you use the idea that the anomaly can be canceled by a local term in one dimension higher, that local term is non-dynamical. So that doesn't flow under changes of scale. Okay, so so we get some conclusions. So let's see if we can justify these conclusions. So one conclusion. Any theory with an Tuft anomaly cannot flow to a trivially gapped theory.
Suppose you replace sigma by gij. The same arguments would go through.
Superficially, it seems so.
And so you will conclude that the left-hand side has to be conclude that the anomaly is a topological term.
Yeah, I mean, you might have to, things will get subtle if lambda is also a space-time symmetry, so that these could actually not commute because there's some non-abelian algebra. But if we assume that it's completely internal, I think that's right.
And we know it's true, right? They're all
Yeah.
topological.
Okay, so we get this conclusion, sort of for free.
Can you outline the steps of like
How do we get this conclusion?
All the steps, but can you string them together?
Sorry?
Can you string together the logic that led to this conclusion?
Sure. So we suppose we have a partition function that has an anomaly. So so that means that first of all, the partition function has some gauge non-invariance, right? So z of a plus d lambda is not equal to z of a, and we can't remove it by any modification of the theory, by any change in the counter terms, right? Because we're only defining anomalies as equivalence classes. Now suppose, now we also know that the anomaly is scale invariant. So the infrared theory, whatever it is, should reproduce this anomaly.
I see. You're saying that because you cannot remove the local counter term,
That's correct.
it has to be non-local or not real.
That's correct.
I see.
That's correct. Okay, so we get this conclusion for free, and this is really sort of the heart of the matter. So in later talks, our main goal will be to sort of milk this statement to as much as we can by finding things which are very much like ordinary global symmetries in that they can also have 't Hooft anomalies. There's a notion of coupling to background fields for them, and there's also 't Hooft anomalies for them, and then we get some RG invariance, and we use that to constrain dynamics. That's sort of the name of the game here. Okay, so and I should say that you can get stronger conclusions here depending on the nature of the anomaly that you have. So for instance, if we were studying this example, we can actually get a much stronger conclusion, which is something that Shiraz mentioned earlier, which is that if you have a theory with this kind of anomaly, actually the infrared is gapless. It can't just be, it can't be matched by a gapped TQFT. That's a fun exercise to prove that this contact term that we discussed here, if you actually integrate it, it gives you a non-trivial correlation function at separated points. That's actually the most robust way to prove that. So if you have this non-zero, it means that the 3-point function of j's is non-trivial at separated points. That's not obvious. You have to actually integrate this anomaly equation, but you get an even stronger conclusion. So
Sorry, I don't understand this stronger part. It's the same thing.
no, so here it cannot be a trivially gapped theory. It could be a TQFT. So far, nothing I've said prohibits it from being gapped. Then, if you have a particular anomaly in mind, you could try and investigate whether it means that the theory is actually gapless. And this is one example where you could use the anomaly to prove that the theory is actually gapless. But more generally, the kind of anomalies that will, and for symmetries that we'll be studying, will not have that feature.
I see. Sorry. Just so you're saying you can integrate this to show that there must be non-local terms.
That's correct. So this, to start with, if you vary this, it says something like d mu, j nu, j rho has some delta function, which you can figure out just by taking the variation with respect to this. And now you try and remove the j mu, the d mu. So you try and write a 3-point function at separated points, which has the feature that this will be true. And first of all, you find that you actually need a separated points contribution to do it.
Isn't this just the same thing, same statement as that you cannot remove that
You
thing
cannot remove it, yeah.
by variation of a local counter term?
Yeah. That's exactly what I was saying.
By a variation of a local counter term.
What you're saying is that that S of A that produces this variation cannot be local, right?
No, it's stronger than that. You could have an anomaly, well, sorry. Sorry, no. You're right. In the continuous case, that's all you need. Yeah, because it's continuous. Yeah. That's correct. Yeah, you're right. Yeah.
I mean, it could be that this is local. Anyway, yeah. Certainly, if S of A was local, then this would have to be obtained, removable with a counter term.
And if it's not local, then that means that there's some correlation function that's wrong.
Okay, so I'm not sure how long should I go on for. I can keep going.
1:20 or so is when people start getting hungry.
Okay. Okay, good. So this was all sort of meant to be a kind of motivation and review for what kind of problems do we want to solve and what are the general tools that we're trying to build up. And so now we're going to move on and get into some heavy formalism for a little while. But hopefully I've given you some idea that we're actually going somewhere. Okay. Okay, so we'll start the next section, global symmetry and topological operators. So the theme of this section will be that we saw, for instance, that for continuous global symmetries, we all know that we can do everything we like with the Noether current. But if we're going to generalize global symmetries to, say, discrete symmetries or later higher form symmetries or higher form discrete symmetries or other fancier things that we might yet invent, we're going to have to move away from the current. Because, for instance, discrete symmetries don't have currents. So we need a way of discussing symmetries that works both for continuous and for discrete symmetries simultaneously. So that will motivate the discussion here. Okay, so let's start with we'll build it up from the continuous case. So we'll start with the charge. So for a continuous global symmetry, we always write the charge in this way. And instead, we can consider the charge on any manifold. So let's imagine here we're in D space-time dimensions. So any D minus 1 manifold. How will we write it? Well, this will be equal to the integral over m d minus 1. And instead of putting J0, the covariant thing that you put is star of the current. So this, since the current is a 1 form, this is a d minus 1 form. So it can be integrated over a d minus 1 manifold. And this charge would give us the symmetry action, say, on the Hilbert space if we cut space-time on this spatial slice. So let's note that divergence of J mu equals 0 is completely equivalent to d of star J equals 0.
So this is just a rewriting of that. These two equations are just the same.
This and this?
Yeah.
This is equal to this in the special case where md minus 1 is space. Right? This is slightly more general in that I've showed you how to define the charge for any manifold.
So for a Q-form field, you will just the dimension of the space manifold will decrease by Q.
Yes, we will eventually discuss that. Maybe not today, I guess, but indeed, if it were Q-form fields, you can see how to adjust all the codimensions.
I was just wondering about your second statement. That what will be the Hilbert space statement then? Like in this case, you said that if you cut on this space slice.
Yeah. So here, if we think of the space as space-time as md minus 1 times r, this would tell us how the charge for our global symmetry acts on that Hilbert space. The Hilbert space quantized on md minus 1.
And when you have Q-form field, then how?
So then you'll get operators. It'll be more complicated. Yeah, I mean, let's come to it later, actually.
So are we in Lorentzian space or Euclidean space in that second statement? Are we now in Euclidean space see the difference between those two. In Lorentzian space, you'll always want a space like manifold, right? Or not?
No, that's
Space
correct.
like
That's correct. Yeah. Sorry. Maybe it was because here what I implicitly had in mind was just R d minus 1.
Okay.
That's what I meant.
Okay.
Yeah. It's true that in this part I'll probably more sloppily go into Euclidean signature.
Yeah, then it's genuinely different because you can.
Well, right. So I'm going to discuss the wrapping now. Okay. It's here. Okay. So so we can also consider. So this was the charge. We can also consider the exponentiated version. I'll call U alpha. It depends on this manifold. Let's call this Q of md minus 1. So here we could put e to the I alpha Q of md minus 1. Okay, so this alpha is a group label now. So we're in the group. Okay, so what is there to say about this? So the first thing is what are some properties of these operators? Well, the most important property is that this U alpha of md minus 1, we can ask how does it depend on this argument, this md minus 1. And it depends in a very mild way. So this operator is topological. Meaning if I modify md minus 1 by a small perturbation, this operator, the correlation functions of this operator don't change. Why is that? Well, it's really because of this condition. So if we here have, say, the integral over md minus 1 of star j, we consider a small perturbation m tilde md minus 1 of star j. We can use Stokes' theorem to write this as the integral over some d manifold xd that interpolates between these two of d of star j, and that's 0. Okay, so that's the first thing. So the fact that this operator is topological is tantamount to current conservation.
And the fact that d star j is 0 only in regions where there's no additional insertion.
Yeah, so I'm coming to that. Right. So this is true in a small deformation. What do we mean by small? Small means it doesn't cross any other insertions. So more generally, if we have a charged operator, so these operators implement the symmetry action. Okay, so now let's be really in Euclidean signature so we can draw the picture that Shiraz wanted. So what's the picture? Okay, so we can consider, say, a sphere, a d minus 1 sphere. And inside that sphere, we can put a local operator. Oh, at the origin. And we could, so on this d minus 1 sphere, here we'll put this u alpha of sd minus 1. And the claim is that this is equal, so I can remove this u alpha. And here I just get e to the I q of O times alpha times, again, this local operator sitting at the origin. Okay, how do we see this? Well, it really follows by trying to do this and remembering that there's this contact term in the Ward identity that d star j contains a delta function at the origin times the charge of the operator O.
Sorry, what was this? You just inserted, you took SD minus 1 at time.
So now we're in Euclidean signature. Let's be in Euclidean signature. So we have SD minus 1, and at the center I put a charged local
Yes.
operator.
Okay.
And now I try to remove the sphere. So the sphere is, if the operator were gone, the sphere is topologically trivial. So I could just shrink it down and collapse it using the topological property. Here, I can do that if I first move it away from the operator. So the only issue is that when I move this sphere across this operator, I'll encounter this violation of the closure of star j, and hence I'll get this. Okay. So we haven't really done anything. I mean, these use so for continuous global symmetries. The behaviors of the U's are equivalent to current algebra. After all, I defined them in terms of integrals of the currents, so it's clear that I'm not really gaining much. But their main advantage is that for discrete symmetries, the U's are still defined. UG for G in our symmetry group still makes sense. So you can think of it, if you have a discrete symmetry, as just saying that the discrete symmetry means you have certain domain walls. So here's your UG. And you could have an operator O here. And the defining property of this domain wall is that when we move, first of all, it's topological. And when we move a local operator through the domain wall, it gets transformed by the global symmetry. So that's just this statement again. OK, so
how would I construct this UG? Let's say I have a Z2 symmetry. I don't have this Noether procedure anymore to construct it, so how do I go about constructing this UG?
yeah, so good. So it depends on what you're given. So imagine you have enough knowledge.
I have a Lagrangian with
Yeah.
a Z2 symmetry.
Yeah. So then let me answer it in 30 seconds. Okay. So okay. So we see that global symmetry, having an ordinary global symmetry, is equivalent to having some topological operators with some certain properties.
Is this UG an integral over something local?
No. No, it will have no alternate definition. It'll just be some abstract domain wall in your theory.
But what I'm trying to understand is if I know what UG is for a flat surface, does that define it for a...
Yes, because it's topological. You can try and to locally modify the shape. Yeah. Okay. So so let me, before answering your question in a better way, let me say that. Yeah. Let me say if I'm going to define symmetry in terms of the existence of these group symmetry defects, I should tell you some basic properties, like what does it mean to say that the symmetry forms a group, for instance? How is that reflected in the properties of these UGs? Yes. Yeah.
Question pertaining to something that you said earlier
Yeah, please.
about the deformation of this surface and how things are unchanged because of the Stokes theorem. So if I were to do the same thing in a topologically non-trivial manifold, right? You also said that this particular surface where the charge is defined should be thought of as a charge acting on the Hilbert space defined on that surface, right? But now imagine that there is some non-trivial topological manifold and there are two slices of it which are covariant, right? So that I can have some interior in which I can do the Stokes law to say that nothing happens and the integral here should be the same as integral over here, but a priori this covariatism can be non-trivial. In particular, these surfaces can also be non-trivial. In
Mhm.
How does that become consistent with the statement that things that are not changing are thought of as an action on two different Hilbert spaces? The simplest example perhaps is the pair of pens, where you have Hilbert space associated two circles on this side and Hilbert circles
But
on
I
this
don't
side.
think it's enough that it's. Well, maybe it's enough that it's.
Could that qualify as a small difference?
It qualifies as small if there's no insertions in
Yes,
there,
still
but
use the Stokes theorem.
yeah, you can still use Stokes' theorem. Uh, your complaint is that the Hilbert spaces look different, so how can we compare the operators?
Yeah.
What would be the statement that the action of this generator on the product space here will be the same as the action of the generator on that? Like you get a phase.
But the
you get
product
same
space
phase.
here is different from that space here.
Right, but it's just like if you get a whatever psi is, if you get e to the power I theta psi, you'll get the same e to the power I theta psi.
If size, the Hilbert spaces are different, how can I compare the action of?
But I think the cobordism that you just defined probably also defines a map between the two Hilbert spaces.
I see. So you use some sort of a topological dictionary.
Yeah, well, if it was certainly that would be true if it was a topological field theory. I'm trying to see if it's more general. But I would guess that I think that just the partition function on that manifold with boundary defines a map from one Hilbert space to the other, which is why you can compare them. Because it's got two ends, so it defines a map between the Hilbert spaces.
Sorry, just going back to my previous question, and you're going to say this, but just to clarify, if the way you would define this wall is just to do the symmetry transformation to the left of the wall.
Yeah.
Okay.
Yeah. Good. Okay, so what is the group law? So
So in the Isaac model, you just flip all spins to the left of the wall.
yes. Yeah. 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 Good. So what is the group law? So our philosophy here is we're trying to define the notion of symmetry now in terms of this UG. And the advantage of that is supposed to be that, for instance, we can talk about the UGs for discrete groups, whereas we can't talk about the currents for discrete groups. So we'd like to encode everything in these operators. And the first thing we should encode is the fact that the symmetry forms a group. So how do we see that? So the group law means another property of these symmetry defects. It means the existence of junctions. So we can have, here will be three symmetry defects. Let me orient them. There will be a junction of this kind whenever G1 times G2 times G3 is equal to 1. So these here, this is a drawing of UGs for various Gs, and they can form a junction. This is equivalent to a fusion algebra. So we can have G1 and G2, two domain walls, and if we bring them together, we get the domain wall for G1, G2.
Sorry, to go back a bit. So if you have a Newman symmetry, I know how to define UG as a loop, like as an operator, like in the Hilbert space, I know how to write down UG as an operator, which is just an integral over the surface, right? But say you take a Ising model and it's a kink operator, like it creates a kink. It's somehow an operator that acts on half of space, right? It is not some operator that's just localized to the line, to the surface you're drawing. Somehow, it's somehow very non-local. Like,
It's not.
is there a way to, like in a discrete
maybe you're confused by the thing that Shiraz said about the fact that it looks like you transform all the spins to the left. But since it's a global symmetry, if you had transformed them all everywhere, you wouldn't say that you did something everywhere in space-time, because that would be a trivial operation, because it's a global symmetry. So the fact that...
I think you think of that direction as time, right? I mean...
Yes,
you
exactly.
do- yeah.
Yeah.
So if you think of it like this, you've done the transformation up to some time where you're measuring the charge. I think even in the continuous case, if you think of it as slicing time, that will probably...
Yeah, that's a good suggestion. Yeah. So think of the transverse direction as time, right? When we were thinking so.
But then base, but
Okay. Good.
then
Operate.
Yeah. You do something once. Okay. So in that spirit, let me now say.
Sorry, can I just, regarding this thing about Z2 and you not having currents, I don't know if this is possible, but like if you have a discrete symmetry, can you lift it to like a continuous thing and then like use a gauge principle to say that you only want to keep states that are like Z2?
So you can do that just formally at the level of Zn gauge fields. You can do that. So for instance, at the beginning of the talk, I discussed an action for Zn gauge fields. That is such a continuum lift, right? So I lifted a general Zn gauge field which doesn't have any differential form representation to a continuous field. But the problem is that you will not in general have any prescription for coupling that continuous field to your actual quantum theory. So there's no real way to make that work in general. So you can do it just at the level of the gauge fields themselves, but not at the level of coupling them. Because your system doesn't actually couple to a U1 gauge field. It doesn't know how to do that. Okay. So we talked a lot about background fields. So let's keep going. So what are these UGs in terms of background fields? Well, they basically are the background fields. Symmetry defects. Yeah.
what's the arrow for your removal?
Orientation.
Oh, G3 to 23 was the other way.
Sorry?
G3 to 23 was the other way.
Yeah, exactly. Yeah. It just to so imagine you bring an operator through here and you make a oriented direction with the operator motion vector. You want to make sure that the whole thing is consistent. So here, if we went down this way, say, what would we get? Starting with an operator, we'd get first G2 on O, and then going through here, we'd get G1, G2 on O. Now we want that to be the same as if we went here. And here they'll be unoriented, so this should be G3 inverse on O. They'll be oppositely oriented. And that is correct.
Sorry, the statement is you can have a junction only if this condition is obeyed. Right? You can have a junction between G1, G2, G3, provided G1, G2, G3 is equal.
And also necessarily it exists. There exist junctions.
There exist junctions.
Yeah, yeah.
So what does this mean, there exists junction? It's something that I can define more clearly. What does it mean? It's not a dynamical object that exists in the field.
It's not a, so I think part of this will be answered when I connect to background fields. So let me try and do that and then ask again in a minute. So
You're saying there is a well-defined operator
Yes.
of this form
Yes.
whenever G1, G2, G3 is.
that's correct. Yes. There might be choices, but there definitely exists at least one. Okay. So symmetry defects encode.
Well-defined operators, which ones are you referring to?
This thing. The fact that you can draw this picture. This picture always exists.
Okay.
Whenever G1, G2, G3 satisfy this
I see.
this condition. Okay. So so what are these symmetry defects? Well, they just encode background gauge fields.
Sorry, just the symmetry defect is then the operator at the center? Is that what
No,
you're-
sorry.
that's what
Symmetry
you're looking for?
defect is this term is synonymous with UG.
UG, okay.
Yeah.
So is there an analog of these junctions for the continuous symmetry?
Yeah.
You can just define that for any three.
Yeah. For any three phases that satisfy this, you could do that.
How come I've never heard of them?
No, you probably have because, let's see, do they have a different name?
Have I ever, is
Yeah.
there a classic use for these things for continuous?
Well, as I'll about
It's
to,
about trivial for continuous.
this may look very fancy, but it's really just a way of saying that you can couple to general background gauge fields.
Is there some classic use for inserting this kind of?
Yeah. So I'm going to draw a picture where we're going to. Okay. So symmetry defects encode background gauge fields. What does that mean? Let's do several examples, and then we'll say the general statement. So suppose we want to take the trace over the Hilbert space on MD minus 1, where we put a symmetry action G in the Hilbert space. What is this equal to? This is the partition function on MD minus 1 times S1 with what inserted? With UG inserted at a point on the circle. So that's the example related to what we were just discussing. So this is, what did we do? So we actually put a flat background G gauge field, which has some holonomy around the circle. And we could encode that by saying just stick UG somewhere. So UG, when I say, I made a slight imprecision here, when it encodes symmetry defects, when symmetry defects encode background G gauge fields, these are necessarily flat. So if we have the idea that we're really interested in using this formalism for discrete symmetries, that's all the gauge fields. But for continuous global symmetries, there would be more background fields that we can't describe in this way.
Yeah, this would be the same as putting a Wilson loop in the representation G along S1, right? This trace would give A0.
Yeah.
It's a chemical potential.
Yeah.
It's a chemical potential.
Yeah.
I'm just saying,
Exactly.
UG as a given instant of time
Yeah.
will make A0 jump because it's the
Exactly.
conjugate.
Yeah, exactly. Yeah. Okay, good. So let's do a more interesting configuration where we need to use the junction. So in general, you need to use junctions to describe, to encode background gauge fields in symmetry defects.
Do you think beta minus beta h in the equation, or have you substitute one in some way?
Sorry?
Would there be an beta minus beta h in that equation, or not?
Oh, probably.
I should write about it.
Sure, yeah.
For non-linear symmetries, when you define UG, it just depends on G. There is no representation there.
There's no representation, it just depends on G.
While on the left-hand side, would you not need to specify the representation on the Wilson loop?
Here? No, the Hilbert space has some action of G on it. That's just part of the data of the theory. Okay. So more interesting backgrounds.
How does it look like in terms of conventional insertions of Wilson loops? Just some overall representation?
No, this is a background gauge field. So we just have some background gauge. So if we were in the continuum, as we were just saying, we'd have some A0, which is something. And the integral of that would give us the G.
You take the kinetic term of every field. Every field is in some representation. You turn on a flat connection for that field in that representation. That's the same.
You're doing this all the time when you're computing indices. Okay. Okay, almost done, I promise. Okay, more interesting backgrounds need junctions. So let's give an example. So suppose we're in 2D and we're considering a partition function on the torus. So a typical thing we might try to do is turn on commuting holonomies around the two cycles. how would we represent that in terms of symmetry junctions? In terms of symmetry defects and junctions. So first we'll draw a torus. Okay, so this is just the sides of the torus. Maybe I'll change colors to make it more clear. Okay, so okay, that's horrible. We won't do that anymore. Okay, so we want to have G1 and G2 as we cross. So let's say we put G1 here. So we have to put G1 here. So that has the feature that if we pull a charged operator across this way, we get a jump by G1. So we've succeeded in getting a jump by G1 this way. But to get it, now we want to get a jump by G2 if we go this way. So okay, we better put G2 here. Therefore, G2 is here. That works if we go through here. But if we go through here, we need a more interesting combination. So here we put G1, G2, inverse, like that. And now you can check that this is a consistent configuration, which has holonomy G1 this way, holonomy G2 this way. And it only works provided that G1, G2 equals G2, G1. That you can check by here there's a condition for this junction to exist, which is that the cyclic product going around should be 1. Here we need the same condition to be true, but you'll find that it will only work when this is set up.
You solved one of those conditions by writing that as G1, G2.
That's right.
But the other one that has to
Yeah, that's right.
work out.
That's right. That's right. So, okay, so this is how we would describe. So,
Sorry, and if you just wanted, the simplest configuration would be where there's that middle.
an X. Yes, we'll come to that in a minute. That's important. More questions though before we come to the X? Okay, so good. So
So I missed something. Where did you use G1?
I use this to make this and this simultaneously compatible because I need that the cyclic product of the things going around is 1. That was the condition on the junctions.
Yes, yes.
But there's some tension between saying this one is correct and this one is correct. And right, exactly. In order to get it to work, I'll need that. Okay, so in general, what's the statement? So a general flat background G gauge field is a net of these symmetry defects, where a net just means an arbitrary configuration with these trivalent junctions.
Sorry, and it's because that you get different condition because when you go that way, it's unoriented, whereas when you go that way.
Yeah. So the initial junction thing that I drew was with all the arrows going in, going cyclically around. It's G1, G2, G3 is 1. And then if you have the arrows going out, you need to put inverse and.
Oh, I see.
Yeah.
That flips some order.
Yeah, exactly. Otherwise, it's G1, G2 has to be that. It's also G1, G2 has to be that. This guy is in for this and but out for that.
Yeah. So it's actually G2, G1 for
Ah.
and then okay.
Okay. So right. So what is the moral of this discussion? The moral of this discussion is that if we want to discuss symmetry defects, these abstract operators, it's completely equivalent to discussing flat background gauge fields. Every flat background gauge field can be described in terms of some configuration of symmetry defects, and conversely, every configuration of symmetry defects is some particular flat background gauge field. So that's a kind of invariant way of answering your initial question, Shiraz, of how would you how do you define this defect for the theory? How would you know how to study it? Well, if you actually have a Lagrangian which say has a Z2 global symmetry, you should in particular know how to put a Z2 background field.
Why do we have only 3-point intersections, not 4 and this?
Yeah. So let me finally come to that. Okay. So we'll close with this last little remark. So I spent the whole time talking about at the beginning talking about 't Hooft anomalies, and you could ask. Where is that in this story, and what kind of, what's sort of the nature of that? So let me just flash something here. So if we have a configuration like this, So you can always resolve an intersection like this into 3-point junctions. So we could resolve it like this, or we could resolve it like this. Okay, so these are two different resolutions of the cross into 3-point junctions. So clearly it's sufficient if we know these 3-point junctions. However, there's a subtlety. Maybe how do we know that these things should be equal, right? We would like this resolution to be unambiguous. We would like, and in fact, you can check that these two configurations of symmetry defects differ by a gauge transformation.
Just to make sure, when you're resolving it, some two are coming together and the other two, right? I mean, that's what's going on, right? The way you drew it, or what was the way you drew it? Didn't you take the up and the left in both cases to come together?
Did I?
So it's just that the arrow, the middle arrow went vertical or horizontal, but I'm not sure what the significance of that is. Or did you mean to take other sets together?
Did I do something wrong? Let's see. So
no, I just wanted to
maybe I did something wrong. So this.
You want another.
Oh, sorry. Maybe I wanted the other two. So
okay.
yeah, let's.
Yeah.
Well, but I should draw it better. Let's see. What should I have done here? Right. So I should have drawn. Like that. Now there's something different running in the middle. Yeah. Okay, so in fact, these two configurations of symmetry defects actually differ by a gauge transformation. What does that mean? So as we saw, current conservation or gauge invariance, which is the same as current conservation, means that the operators are topological. So I should just be able to move these up and down willy-nilly. There's no other insertions here, so I should be able to change them. So indeed, that means that these two things should differ by a gauge transformation. But there could be phase ambiguities, right? So an 't Hooft anomaly in this language will show up as phase ambiguities when we try to compare these two signs. So strict gauge invariance in the presence of the background gauge field would mean that the correlation functions in the presence of this configuration of symmetry defects is exactly the same to the correlation function in the presence of this configuration. But an 't Hooft anomaly would mean that will not quite be true, but there will be some mild violation, some in particular phase that will show up when we try and do this manipulation.
So how do you see that?
How do you see it? Well, I'm not really claiming it. I'm just asserting it right now. I'm not really proving.
Suppose these were continuous symmetries. Then in that case, you should be able to just systematically show it.
Yes, except for the fact that everything is flat. So I'm a little worried that for the standard 't Hooft anomaly, which has the curvature, it might you probably won't detect it at all.
Wait, so this statement is not true for the continuous case?
I think that for the continuous case, you need to study background gauge fields with curvature to detect the anomaly.
For this particular manipulation, you don't see ambiguity.
That's correct. So these symmetry defects only give you access to flat background gauge fields, which is everything you want to study if the symmetries are discrete, but is a kind of limited subset if the symmetries are continuous. And I think that the anomaly will only show up with a non-flat background field. If I'm.
We didn't talk about 't Hooft anomalies for discrete symmetry. We didn't quite talk about it.
We didn't talk about it, but so I'm sort of telling you what it means right now.
This is your definition.
It will be a phase ambiguity when we try and do a topological manipulation of the defects, modulo something. So I have to tell you what it's modulo and so forth. But maybe this is actually a good place to stop, since we're.
No, but if this is so different from the continuous case, why do you call this why do you use the same name for this in the continuous though?
Because it's a violation of gauge invariance. So the original Tufte anomaly said that if we had a background gauge field and we did a gauge transformation, the answer was not the same, but it was a controlled violation. And the point is that these two configurations, since they differ by a topological manipulation, are actually related by a gauge transformation. So this is again saying that the partition, so we could consider the theory as a functional, in the presence of a flat background G gauge field. And we could ask, is it gauge invariant, the partition function? And that's equivalent to asking for the questions like, if we change the order here, do we get literally the same thing or not?
So in the continuous case, you won't have curvature sort of concentrated at the vertices? Or not? So I mean, some Stokes theorem kind of thing. I can't see it. But
No, I can't see it either. Let me think about it. I'll try and get back to you.
If G1, G2, G3 were to be not 1, then
That's what I guess, yeah. Okay, so let's stop here and we'll continue tomorrow.
That was really great. Thank you so much.
You're welcome.
Very
Ronan
clear.
has a question.
Sorry.
Oh, we should ask.
Why is this configuration equivalent to flat gauge field? And in the discrete case, what is a flat gauge field?
Well, should turn it around. You should ask what's a non-flat gauge field. So in the discrete case, every gauge field is flat.
What does this mean? What do these words mean?
What does flat mean? It means it has no curvature.
There's no H in the discrete case, right?
Hence, it's flat.
I think it would be useful to discuss what these terms mean.
What these terms mean? Well, okay. As you said, the concept of non-flat doesn't really exist for a discrete gauge field.
What property of flat and continuous carries over to discrete?
A flat continuous gauge field is extremely similar to is the kind of thing that we're talking about here. Flat means vanishing curvature.
You can't define a curvature in a discrete case.
Right, but in the
But on the lattice, one can.
Lattice, I know what it means, but he's talking about
a discrete gauge field just does not have any curvature.
It doesn't have a concept of a parallel transport and defect and like holonomies and stuff.
It has holonomies. Yeah, that's correct. That's what these are doing. So when you cross this, you get a holonomy related to the element G that lives there.
I see. So you wouldn't attribute that to.
But there's no curvature.
We always come back to.
Yeah. If you go right, if you go in a loop, you come back to yourself. That's right.
That's because we can take the loop to very small and essentially be at the same point. Unlike lattice, for example, then you could have one bracket.
But I could still ascribe that to delta function curvatures. I mean,
Yeah, I know.
I just think that if you have a G-valued connection where G is a discrete group, there's no concept of curvature of that thing.
But maybe just to clarify the question, going back to the continuous case.
Yes.
To try to understand as clearly as possible why you say that this is all flat. And this is basically because
It's Abhijit's assertion that the reason that the junctions that I'm talking about have G1, G2, G3 is 1. So the parallel transport in a loop always takes me back to myself. So that's how you locally measure the curvature, is by doing small parallel transport in a loop.
But you could conceive of a junction, no? Where you don't.
I guess you could you could in the continuous case. I don't.
Not even in the discrete case. What's the issue?
If the left and the right of the junction are defined by doing the symmetry transformation, by doing the G1 symmetry transformation to the left, then it wouldn't make sense. It just won't come back to itself.
But that type of thing you always do, right, in the continuous case, so then you don't come back to all cells.
No, but what does it even mean? Suppose your definition of this wall is do the symmetry transformation to the left. Then if that doesn't give you a well-defined procedure, that's the only definition you have. And then if it doesn't come back to itself, it doesn't mean anything. Is that right?
Yeah, I think that's right. I mean, and I think the mathematically parallel statement is that for a discrete group, there's no concept of curvature. There's only a connection. It's tautologically flat. There's no curvature.
Here in the toric code, I can define states where a placket has a non-trivial P. Yeah, a non-trivial with a loop around it.
All of the last week I heard questions like in the toric code. Somebody tell me what that
Sure. The toric code is what?
It's a Z2 gauge
No,
theory on the
it's not a Z2 gauge theory on the lattice. It's in fact not that. That's exactly what. Yeah. It's yeah. The whole claim to fame of the toric code is that it is a lattice model without any gauge fields. There are no gauge fields in the toric code, but it has the very special, interesting property that in the infrared, it is described by a Z2 gauge theory. So, for instance, the Gauss law constraint in the gauge theory is not imposed in the ultraviolet. Instead, it comes out by some energy considerations. That's the claim to fame of this thing, is that you get emergent gauge fields.
So you put an energy cost to any field that violates the Gaussian.
Exactly.
Okay.
That's it.
Yeah.
Like you can define states which has a non-trivial.
That's true, but there's no gauge field. Until you're in the strict zero energy limit, there's no gauge, right? There's no lattice gauge field there.
I take the quotient of the Gauss law to infinity. That was that to be achieved, correct? Or maybe
Sorry, maybe we should ask Allahabad, have they gone?
They're all gone.
Ah, okay.
See, if you take the quotient of the Gauss law to infinity, it's a Z2 gauge theory on the lattice.
Okay, so we can just discuss, let's just discuss lattice Z2 gauge theory. That's what you want to discuss.
Yes.
Okay.
I can define a configuration where the sigma z's around a placket do not multiply to 1.
I don't,
This is not non-flat gauge field in that sense.
I don't think
It's
you
like
can do that.
P dot dA on a little square is not 1.
Okay, I'm not answering this question very well, but I really think that you can't do that.
The states are there.
The
These
states are there.
magnetic anyons in the toric world. And like you don't need the electric sector at all. This part exists.
Wait, can you say it in a way that removes the extra lingo of magnetic anions and things like that?
No, okay. These states are there because they're not prohibited by Gauss law.
So when you say Z2 gauge theory, you mean that you have you now have link variables that are Z2 gauge fields,
Yes.
which are not in the those are not in the toric code, right?
I mean,
There's no such
the
variables. That's the whole point of it.
zero relation space, like if you send in toric code, if you send the quotient of the Gauss law to infinity, you get the Hilbert space of the Z2 gauge theory.
So is the toric code important for this?
No, it's just
okay.
that I
So
know
this
the
is not
toric.
about Z2 gauge.
Please, yes.
Yeah, so this,
So-
yeah.
Yeah, Z2 gauge theory, the configuration, so the product of the 4 sigma z's around a loop, around a little placket, commutes with the Gauss law, so it can be either +1 or -1.
Product of the force.
And it's perfectly fine. the product of the sigma sets is the discrete analog of a Wilson loop, which is like B dot dA.
Yeah, but sorry, the thing that isn't the thing that you're talking about the Wilson surface of Z2 gauge theory, not the flux. I think that's.
V2 plus 1
Oh, okay. 2 plus 1 dimensions. Then we
My suggestion is we continue this overlap.
yeah. Let me think.